Hi, math students. It's Miss Carol again, and we are working on Algebra 1B, Project 1, Lesson 3. And in this project, we are still working on quadratic equations, but we're putting it into a very practical application of a basketball shot and the trajectory that a basketball would follow from the time it left the player's hand into the basket. Okay, so here's our scenario. A real-life situation that can be represented by a quadratic equation and a parabola is the height of a thrown object. Janelle is in the community basketball league. Her typical shot is from 6 feet at a velocity of 20 feet per second. Use your knowledge of projectile motion and graphing quadratics to answer the questions. Okay, real quick, I do want to clarify here that this 6 feet is not, let's say that this is our basket that's 10 feet, okay? So that's at a height of 10. This 6 feet is not a horizontal 6 feet away from the basket. It's actually a vertical height of 6 feet, okay? And that's going to come into play. So basically, she could be 5 feet from the basket, she could be 15 feet from the basket, but she's always going to release that ball at a height of 6 feet, okay? So let's just jump in and answer these questions. What is the initial velocity? And this little subscript 0 here, the way we say that is V naught, or V initial velocity. If you ever hear someone say V naught or H naught, they're referring to initial values. So the initial velocity, they told us right here, is 20 feet per second. Okay, velocity is a speed. You could have miles per hour. You could have seconds per hour if you're dealing with like a snail or something. Those are velocities. So it's a distance per time. And this is the only one that kind of fits the bill there. Okay, next one. What is the initial height? This is what I just described to you. So every time she releases that ball, she's going to release it at 6 feet high. She's not releasing it at a distance of 6 feet away from the basket. She's at a height of 6 feet. Okay, so that's our H naught, or our initial height. All right, the height of a projectile over time is given by the standard. You will see this again. The standard equation, h equals negative 16t squared plus v naught t plus h naught, where v naught is the initial velocity and h naught is the initial height. What is the equation that represents the height h of Janelle's shot over time? So this equation is simply this, with the values that we just identified plugged in for V naught and H naught. So H equals negative 16t squared plus 20t plus 6. Okay? Another way that you might see this written is H of t equals negative 16t squared plus 20t plus 6. And sometimes when we do t's, I try and put a little tail so you can tell the difference between that and an addition sign. This h of t simply means that our height is a function of the time. So our height is changing based on how long that ball has been in the air. Okay? So hopefully that makes sense, and we will we'll dig into that in just a moment for this next one. Okay, use the equation you just wrote to fill in the remainder of the table for the given values of t. So what's happening here is that we're being told at a height of 0.25, or excuse me, at a time of 0.25 seconds, we don't know. We need to calculate our height. But we do know that at a time of 0.5 seconds, our height is 12. At a time of 1 second, it's 10. And at a time of 1.25 seconds, it's 6. Okay? We also need to find 0.75 seconds and 1.5 seconds. So to get those, I'm going to use that h of t that I just wrote out, but let's do it again. H of t equals negative 16 t squared plus 20 t plus 6. So now I'm going to write h at 0.25 equals negative 16 times 0.25 squared plus 20 times 0.25 plus 6. So all I did there was I took that value of t that they gave us and I plugged it in every time I saw a t in my quadratic equation there. So now h at 0.75 equals negative 16 times 0.75 squared plus 20 times 0.75 plus 6. And last but not least, h at 1.5 equals negative 16 times 1.5 squared. Oh, I better log back in there. Not idle. 1.5 squared plus 20 times 1.5 plus 6. And now I can do each of these calculations. When I do the first one, 0.25 squared times 16 negative, gives me a negative 1 plus 20 times 0.25, so plus 5, and then plus 6, so plus 11 basically, is 10. So my h at 0.25 equals 10. 0.75 squared times 16 negative is a negative 9, plus 20 times 0.75, which is 15, and 6 is 12. And last but not least, h at 1.5 so that's a negative 36. That first term is a negative 36. 20 times 1.5 is 30. And so negative 36 plus 30 is a negative 6 plus 6 is 0. So h at 1.5 is 0. Okay, so you'd enter in your answer like this. But I want to show you something really quickly. I think it's really cool. I'm going to just go over to this screen here. I've used something called MetaCalculator. I like it. It's a great graphing tool. All I did was I had to use y and x instead of h and t, but I just plugged in that equation and then I scrolled down and hit graph. And this is what I ended up with. And so you can see right here where that graph crosses the x-axis at 1.5, my height is 0, okay? My initial height, where at my time 0, remember she's letting go of it at 6 feet high, so that's why it's crossing the y-axis at 6. Okay, this down here, this other root where it crosses the x-axis, that would be a negative value of time. So that we're not really going to use. But I would think that the other important pieces of information here are that we're going to have our vertex up here at about 12 1/4, 12.25 or so. And that's going to happen at just under a second. Okay, so when we go look at that table, the values should correspond. If I were going to plot these points here, okay, I have my initial time 0 height of 6, okay. I knew that A is 10, so at 0.25, okay, I'm up here at 10. So we've got a point right here. Let's see, at 0.5, I'm up at 12, okay? And then at 0.75, I'm right back exactly at 12 again. So somewhere between 0.75 and 0.5, I crested at probably 12.25. Then at 1 second, okay, I'm back down to 10. And at 1.25 seconds, I'm back down to 6. And at 1.5 seconds, let's see, that was 1.25, and 1.5. It's not a perfect picture there, but I'm all the way back on the ground at 1.5 seconds, okay? So what you can see here is that parabolas are symmetrical about the vertex. So I'm going to scroll down with this, and we're going to just answer this next question. Which of the following ordered pairs are points that lie on the parabola that graphs the height of Janelle's basketball shot? So we know that at 0.5 seconds, she was up there at 12 feet. So that first one works. 0.25 seconds, she was at 10. And this is from the table on the previous problem. 1 second, she was at 10. Okay, 1.25 seconds, she was at 6. 0.75 seconds, we calculated again to be 12. 6 seconds would be way out here and way away from our parabola. So that is not something that's going to work for us, okay? 0 seconds is right here. She's at 6 feet at 0 seconds. She's not at 1.5 feet. She's all the way up at 6 feet at 0 seconds. So that one doesn't work either. And then at 1, this is the only one that might be kind of tricky if all you were looking at was a graph. At 1 second, remember, she's at 10 feet, not 6 feet. At 1.25 seconds, she's at 6 feet, okay? So if you wanted to use the table, you could do that, and you could also do something like this online graphing calculator to kind of help you visualize what's going on at each time. You can figure out the height, and then you can remember that it's symmetrical, okay? Hopefully that all made sense. Okay, we're going to move to the last question here. Describe what the graph of the parabola represents. The height of Janelle. Describe what the graph of the parabola that represents the height of Janelle's basketball shot looks like. Provide as many details as you can, such as the points on the graph as well as the shape. Okay. How does the graph relate to the context of what actually happens to the ball? So I'm thinking it actually relates really well. I think the things that you need to point out here are that she releases the ball at time 0 at a height of 6. The ball reaches its peak height of about 12.25 feet between 0.5 and 0.75 seconds. And then the ball is back on the ground at 1.5 seconds. So it's totally back to the ground, not just back to its initial height at 1.5 seconds. And then that is a pretty good representation of something that you might see in an actual basketball game. A shot doesn't seem to take more than a second or a second and a half. And that would be all dependent on probably the player's strength as they release the ball and the initial velocity that they have behind it, because that gravity is going to remain the same. So the things that the player maybe can control are the initial velocity and the height that they release the ball at. Okay, so I will be interested to see what you put here. It'll give me a really good idea of your understanding of what we've done. And if you have any questions, comments, or concerns, just let me know. Thank you.